Well, good afternoon, everyone. Give you a very short overview of what I intend to cover today. And first of all, I'm going to show you a very short video clip of a New York server streaming a video clip. And the streaming of video raises certain questions that we're going to attempt to answer in the talk on compression and file types, and time permitting, I'm going to introduce you to some UDP, which will be useful to have as a background. And we're going to also examine the general topic of multimedia transmission over the internet. And included in that is that of interactive sessions. I mean, how are they possible and what constraints are there on them? So I'm not sure about whether the first step is going to be giving you a first presentation of UDP. But what I will do at some point is just skip through a presentation that shows the structure of a UDP packet, um, indicating the existence of fields concerning port numbers and the length of the data field and the destination and receiver's address. And the reason for talking about UDP, anyway, is to provide a little bit of background in constructing a streaming application and perhaps a receiver application demonstrated in the video clip. Um, so, and I guess the other important, relatively important topic is to discuss your imminent coursework number 2, and hopefully I'll give you a good idea of what's on the assessment brief. And its status is provisional, but I hope to release it very early very early on Sunday or just after the weekend. So the final version should make an appearance quite quickly. So I'll do that. I'll set up the video. So it's very short. And yep. Well, for the coursework, I'm going to give it to you at the weekend, as I said. But I realise that you're going to be busy for exam week in 2 weeks' time, and I think you're going to be quite busy preparing for exams this coming week. So the deadline is 2 weeks after the finish of the exam week. So in fact, it's about a month away. You've got plenty of time. Okay, and I'll guide you whenever you need to be guided. Okay, so I think that's reasonable. Okay, thank you. So I'm just trying to get hold of my video link, and I mean, you might think it's a bit of a boring video clip, but there's lots of things we can discuss about it. So just copying that and getting rid of that. I just hope I'm not going to inadvertently shut the session down. So just got to be a bit careful. No, I haven't. So Okay, so uh, the key thing about the video is the emerging question. Well, how is it possible to stream a presentation occurring in New York in what is possibly real time? I mean, can I interactively participate in it's like a multi-person conferencing session and so on? So I'm going to talk about. I think I'll talk about compression in a moment. Um, but the key thing I want you to know about that video is that I quite like the quality of the video in the sense that it's clearly visible and there's no jerkiness in it. It's a continuous presentation, and in fact, it's an extract of a very high quality um, film production video, and it's actually a compressed version of that that's being used to stream it over the Atlantic. So I'm sort of raising these sorts of questions. The other thing I want you to know is that it's actually using a protocol called RTP. I think I'm going to get confused at that point already. It's RTP, I think it is. And it's very like UDP in the sense that it's an unreliable protocol. In other words, packets that are sent are very highly likely at risk from being lost or delayed. So we're going to have a look at that particular problem because I'm not noticing any conspicuous fault in the continuity of that video clip, and we're going to at some point look at the whole issue of transmitting stream data over long distances. So I'm going to upload a presentation, and just going to have a look for that. And I think that's a bit of a problem here. So it's just a presentation on compression and other related matters such as encryption, and we will actually cover some material on encryption next week. I mean, we're not going to have time to look at it this week. So, and after we've looked at the general issues of file formats and compression, we'll look at the content of the assessed coursework tasks that I've given you. So it's still uploading, and I'm just surprised that in this day and age it takes so long to upload a presentation. So I'm just going to get rid of this page if I can. So I'm getting rid of overview, and so hopefully that's going to disappear any second. No, it's not. Oh dear, oh dear. Might have to try again. So confirming that. Oh dear, oh dear, oh dear. So apologies for this unintended pause. Okay, so here we go. So it is literally, by any UK standard, it's an A-level topic with some A-level material. And what I'd like you to read is up to page 37 for this week's content. And intended learning outcomes is that we're just going to remind ourselves why compressing files is important. You probably know what the obvious reasons for compressing files are and the obvious advantages, but never mind. And I'm interested in showing you or indicating how text and image and audio and video files are compressed. And I want you to become aware of or appreciate the effects of compressing a file. And I want you to know a little bit about the various file formats. And I'm going to give you specifically two compression algorithms. One is called run length encoding, and the second involves Huffman trees or Huffman codes. And next week we'll do a little bit of work on symmetric and asymmetric encryption, but at the moment that's not vitally important at the moment. So file handling is clearly a primary function of a computer system. Almost an everyday use of a computer, we're somehow manipulating files. Maybe we're reading or copying or putting data that we want to put into long-term storage into some files stored on some medium. So just say hello, Farhat. It's good to see you. It's not quite evening, but it's lovely sunshine here in London. So obviously each different file format in which data is stored is going to occupy a range of storage space. For example, an image file with reasonably good quality occupies a megabyte, and a video file perhaps needs to store information gained at 25 video frames per second, and that's going to occupy a relatively large storage space, on the grounds that each frame of video is going to represent a fair amount of data, and you're showing 25 frames per second in a reasonable high quality video clip. So compression methods can and should be used to reduce the file size. I mean, I can't go on filling my hard disk drive with huge amounts of video, as it seems to have happened in the current situation. Compression is also helpful in reducing the download time of an image. And so I think you can see the relevance for my showing you the video clip you've just seen. You know, it's feasible to download and show me a video clip which is being sent from as far away as, I don't know, Melbourne in Australia, in close to real time. And it could be audio, it could be video, it could be both. It could be a huge image. And it's important that this data can be transferred very, very quickly, as quickly as possible. So anyway, concerning compressing image files, an image file is compressed in order to reduce the amount of memory stored to store the file, as well as reduce the time in transmission of an image. So compression of an image, however, also changes its key attributes, such as file type, because in order to compress a file, I've got to identify the format and the type of representation of the data that's being stored in the file. It's going to have an effect on the resolution, the detail of what I'm going to see. It's going to have an effect on what I call bit depth, and I'll explain that term in a moment. But of key importance, we need to understand what lossless compression is and what lossy compression amounts to. And very often, in my experience, that after having learned about lossless compression and lossy compression, people still have struggled to remember which is which. So, take care to remember what lossless compression actually is and what lossy compression is. So lossless compression is when the file is compressed, but the quality of the image remains the same, or virtually the same. And in lossless compression, the information stored or shown in a video, for example, can be reconstructed to its original form. There's no loss of key data. It's the original data is reconstructable. And in this case, you would typically use a compression type of being lossless if the information within a file is very important and should under no circumstance be lost. And I'll give you a simple example of lossless compression here. And I want you to consider what I think is an old English saying, and it's this: it's see a pin and pick it up, and all day you'll have good luck. See a pin and let it lie. In other words, you're not picking it up. Bad luck you'll have all day. Okay. Well, it's a bit like, break a mirror and you'll have 7 years bad luck. It's one of these wise old wives' tales, as it were. What I want you to understand is that this simple text can be compressed by making a table to hold all relevant information that will enable us to compress this single sentence. Okay, this is just a single sentence, but maybe what we're really talking about is Chris Kinberg's 500,000 word PhD thesis. And what I want to do is to transmit it quickly to Melbourne in Australia. And I don't want any of the thesis's contents to be lost on the way. So anyway, let's have a look at this. So first of all, I'm representing all the words in this column, this connected column, that appear in this sentence, and I'm actually picking up words like you will when they occur more than once. So here I've got you will and you will, and I think there's a couple of other instances like all occurs twice at least. But what I want to do is to represent as a proxy for each word a number. So I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 17. 17 different words, and I want you to understand that the representation of the word see, for example, given an ASCII encoding, and if you don't know what ASCII stands for, I'll let you know, and I'll let you have a glimpse of an ASCII encoding table in a moment. In ASCII, though, each character needs to be represented in a computing system by 8 bits. So to represent the word see, I need 24 bits. To represent yawl is going to require 1, 2, 3, 4, 5, 6 bytes. That's 32 bits because I've got an inverted comma here, which has got an ASCII code. 6 bits, so 6 8s are 48. 1, 2, 3, 4, 5, 6. 6 characters, 48 bits. But any one of these indexes, which range from 1 to 17, could be represented by just 5 bits. And I could represent a lot of other different punctuation marks, because 2 raised to the power of 5 gives me 32, so I can represent 32 I can represent 32 characters, alphabetical characters, uppercase and lowercase. Well, not both, but um, lowercase certainly, and some punctuation marks with 5 bits. So, in particular, I need 48 bits to represent this word, and only 5 bits to represent the number, the integer 11. So I've already got a saving in terms of space as far as storage and transmission is concerned. So, and that's, so a text file can be compressed simply by making a table for converting a sentence to a series of indices from 1 to 17. If I've got this encoding, I can easily represent this sentence by a sequence of numbers. Like, first of all, I've got a 1, and then I've got the single letter word A, so it's I'm going to represent 1 followed by 2, and then the word pin, and that's going to be represented by the number 3. So I've got a 1, 2, 3, 1, 2, 3, and that represents the first 3 words of this sentence. And maybe, in a document that has got something like a total of 500,000 words, the table's going to be quite large. So I've just got to be, I've got to think about this method of lossless compression. And I think you'll agree, without going any further at all, that if you give me a sequence of letters and this table, I will be able to convert any sequence of codes back into a corresponding sequence of words. And hopefully those words are going to make good grammatical sense, but it's up to you, your encoding, to make sure that happens. So the sentence I've shown you, see a pin and pick it up, can be represented by this sequence of numbers. And you'll notice that 10 occurs, number 11 occurs twice, look, there and there. And I'm getting quite an economy in saving of bits by using 11 to represent the word "you'll." So I think you'll agree, without doing any formal calculations, that this saves memory by using codes for words that are repeated anyway, and generally for words that would otherwise have to be stored using ASCII. So with a code and index table, the complete sentence can be recreated. So it's lossless. It's a lossless compression technique. Well, how about lossy compression? Well, when a file is to be compressed using a lossy compression algorithm, unnecessary bits of information are going to be stripped away from the original file. Unnecessary bits. Well, you might say, well, what's the criterion for being unnecessary? Well, I'll give you an example. But the advantage of lossy compression is that you get compression, and it can be a fair degree of compression, and the information that's been stripped out is less likely to be noticed by humans. In other words, Chris Kinberg isn't going to notice if what is actually technically unnecessary to contain in the original file is removed. And this type of compression is going to be used for photographs, static photographs, where the information to be compressed cannot be predicted in advance, whatever that might mean. We'll find out in a moment. Okay, so just move on a little bit. So what I want you to know is that TIFF and BMP files, or files having those extensions, refer to raw bitmaps. In other words, raw details about, for example, um, individual pixels, and they are uncompressed image files. And it'll take you a second or two to find out what TIFF actually stands for and BMP stands for. I can't remember offhand what BMP stands for, but TIFF stands for tagged information file format. And I have no clear idea of what the actual format of a TIFF file is at the moment, but I can find out, and I'm sure it'll make good sense, and it just means that I can um, uh, uh, utilize the real data in a TIFF file. And as I said, it's going to represent uh, uncompressed data. So uh, they represent images with the highest possible image quality because they're looking at the raw data, which is the stuff of an image. As you point your camera towards an image, it's going to see things, it's going to analyze things in terms to regions or pixels or something along those lines. And there's going to be no attempt to compress those files. And other file types are PNG files, which is lossless, and PNG formats is useful for transferring images over the internet. And so again, there's relatively high quality. JPEG is a lossy compression, involves a lossy compression type, and you get a high compression rate compared to PNG. So I probably just contradicted myself, but hopefully not. You're going to use JPEG in digital cameras and web pages, and possibly some mobile phones. GIF, you're using a lossless type of compression, but it only compresses images with a bit depth of 8, so it's quite relatively poor quality to begin with. And of course you can use a sequence of GIF images to create the illusion of animated graphics, and you can use GIF files for small images such as logos and icons and so on. And PDF, you've all heard of PDF files. They're compressed in a lossless way, and you can encode both text and graphics within a PDF file. So each one of those file types is worthy of some further investigation and has some sort of interest. Let's think about videos, video clips. For a short while. Digital videos are created by playing a series of images at high speed, and each image contains a fair amount of data, and you're presenting these to the user at high speed. And if you're transmitting a digital video, you should aim at transmitting them in such a way that the play out time can be scheduled so that the play out schedule is observed, and that means just presenting one image at exactly the right time, in time, when it should be played. And you can't afford to lose images easily, and whenever you watch a video, you're looking at what is the result of presenting a huge amount of information per unit time. So a typical high definition video has a frame rate of 60 frames per second, right? And an advanced video is typically going to be of the order of 300 frames per second. And the sampling rate of a video is going to be given in terms of frames per second. In other words, when you make the video, you want to capture data at the same rate, the same bit rate. And it's typically measured in terms of hertz. And just for your information, in case you haven't come across the word, this German sounding word, a hertz is the SI unit of frequency equal to 1 cycle per second. And SI corresponds to the French translation of Institute of Standards in France rather. So SI, it's a sort of standard unit of measuring frequency, 1 cycle per second, a hertz. In telecommunications and computing, a bit rate is the number of bits that are conveyed or should be conveyed to an observant audience or processed per unit of time. You know, if you're making a video, it's important to know what bit rate your equipment operates. I mean, is it at the rate of 5,000 frames per second? And it would be quite interesting to know about the bit rate of the cameras on the Mars exploration equipment that's already on Mars and so on. I mean, some cameras are very, very high resolution and can process data at enormous rates. And I guess there's a big issue with all the data that's being accumulated on Mars at the moment is that all the data should be communicated with back at Earth, and there are cases when some problems might arise and they're mechanical, for which there is some kind of video evidence, and you need to get that data back to Earth ASAP. And lots of interesting questions about compression and compression rates. Will low resolution compression be acceptable, which is relatively fast to transmit back to Earth, or do you actually want a lossless compression technique, which is likely to result in a lesser degree of compression, but is going to not lose any sort of data or anything, but take a lot longer to transmit. So video files also have a bit rate that defines the quality of audio and image. And a bit rate, I guess, is the rate at which the analog world can be sampled, and in sort of low resolution systems, perhaps you're using just 8-bit quality. 32-bit quality, you're using 32 bits per single sample of an analog signal, is going to give you a more realistic picture of the data that's being sampled. And the faster you can do that, so if you can take 1,000 samples a second, you're going to capture an analog signal together with its peaks and troughs in some accurate detail, which might be of immense pleasure, or could be a vital source of further information. You can see the detail of what you're actually taking a video of in great detail, in fact, greatest possible detail. When you compress video files, you reduce the resolution in general, the dimensions and the bit rate needed. Right, the bit rate you're going to instead of 32 bits, you're going to use a lower bit rate. The information given by a lower rate of sampling and so on. Compressing a video may also lead to poor quality and random coloured blocks on the screen. These are called artifacts. And looking at this single shot, single frame of a video clip, I can't see any artifacts in it, and I can't, to be honest, notice any huge degree of difference between the quality of this and this image. So this is an uncompressed, taken from an uncompressed video which used 50 megabytes of storage for 5 minutes, and this is the same video which is after being compressed. It just occupies 10 megabits per second. And artifacts I wouldn't know, quite honestly. I can't see any odd looking blocks of or regions in the image here at all. MP4 and MOV are file types of examples of lossy video file formats. And it'd be quite interesting to actually look at what an MP4 file format is and compare it with an MOV file format and just compare them. I am just quite interested, but I haven't done this in recent years, so I can't tell you at the moment. A lossy video files, so if you make an MP4 compressed video, you're converting from a higher quality video to an MP4. If you've got the converting software, it's going to be lossy. You're going to remove data. And hopefully it's not going to be critical to data at all. So compression is very helpful when it comes to streaming and downloading audio and video files. And a lot of people say it's absolutely indispensable, because I don't want to wait an hour before my favourite American TV series is downloaded and ready for observing. I mean, that's a lie, because I don't have a favourite American video, but it's just an example. MP3 file format is also used for audio compression, and it can offer, I think this is correct, I think I'm correct in saying this, up to 90% of 90% compression, but I'm just going to have to verify that fact because it seems a bit extreme. It seems very low quality. MP3 files are used for storing files in computers, MP3 players, mobile phones. Okay, so if you want to store a video on your mobile phone, and you can't expect a high quality video to be played on what in fact is going to be a lowish quality way of playing a video on a mobile phone. But you can convert CD files into MP3 format using the right compression software. So again, the issue of different compression software available is interesting. And even though the quality of an MP3 file cannot match the original CD file, it's still satisfactory for various purposes, it's claimed. Well, what does that mean? Does it mean that Chris Kimber is going to not notice the relative absence of CD quality in what he plays on his phone? Or what? What exactly? What purposes? Or does it mean I'm going to get a crude representation of what people look like, and that should satisfy me? Because I can recognise that one person as a man and another person as a woman, and so on and so on. I'm not quite sure, but it's something for you to think about. Right? This criterion, satisfactory. Which purposes? What purposes? How are they going to be determined? So we know that lossy compression removes certain information from the original file. And this is connected with the fact that humans can detect sounds in a fairly fixed frequency range from about 20 hertz to 20 kilohertz. And babies can actually hear frequencies slightly higher than 20 kilohertz. And maybe there's some interesting biological reasons for why a baby should can tune into higher rates of sound. But people lose some higher frequency sensitivity as they get older. And the upper limit seems, on average, in older adults, to be close to between 15 and 17 kilohertz. So it's quite a big drop in sensitivity as you get older. And all of that reminds me of my dog, which has got a tremendous hearing range. I mean, it can hear almost hear bees buzzing at the bottom of the garden, and it can hear snakes slithering in the grass 100 meters away, and it can hear certainly cats jumping over the fence, and can hear rats talking to one another, and foxes screeching away at high frequency in the middle of the night, and so on. So the issue of sound frequency and data is a very interesting one, and sensitivity to data. Right. So lossy file compression technique, let's think about that in MP3. The user doesn't hear any difference whilst listening to an MP3 file compared to perhaps a CD copy, because the perpetual musing, shaping in file compression algorithms that only removes details that humans simply cannot perceive. You're not sensitive to all the sounds that might be on the CD, but which humans can't hear. You know, the very, very high pitches, the little squeaks from a violin that you actually find in the concert hall. Most humans won't. Well, most humans cannot hear these very, very high frequency sounds and so on, or maybe very, very low frequency sounds. Therefore, in the case of MP3, only a few parts of the sound file are removed, and those parts that are removed doesn't impact on the overall quality of the sound. But the bit rate does affect the quality of an MP3 file. And the bit rate does vary from 80 to 320 kilobits per second. And an original CD file has a bit rate of 200 kilobits per second, and more than that, in fact. So what am I saying there? I'm saying that bit rates certainly do affect the overall quality of an MP3 file. Forget about the compression part, but the actual bit rate that's taken as the base for conversion does affect the overall quality of the file. And I think I'm not contradicting myself or not saying anything controversial by saying that. MP4 are similar to MP3 files, but allow storage of other multimedia files such as video, animation and photos and so on. And in fact, I'm recording this session as a sort of double indemnity, because the BBB recorder system seems to be very unreliable. I'm using Screenpresso to record a video audio file, and I'm using MP4, and what I'll do with the MP4 recording is to upload it to YouTube, and they'll convert it into a YouTube video, and it's going to be stored. It'll be stored as such, and it's quite a effective way of storing what can be very, very large video files. Um, so video files are also compressed to a stream online in MP4 format. So MP4 is useful for transmitting, and this file can be used for transmission over digital channels and via satellites and via interconnected devices by means of cables. So DVD movies are available in MP4 format. And again, I tried to verify all these claims. I wanted to know what bitrate a high definition 720p video has, and I got a slight variation of this figure quoted. And I want you to have a brief understanding of what a 4K video is. It's a very high definition video. It has a bit rate of between 8,000 and 14,000. So that's 14 up to 14 million bits per second. If you've got equipment to display a 4K video, it's got to be capable of keeping up with that bit rate. It's recorded at this rate, and the equipment should be capable of showing the video with this particular high bit rate. The stream rate for standard definition video is 1 megabits per second, and for an HD video 3.5 megabits per second, and for a 4K HD video 15 million bits per second. So one day I'll get to see a 4K Ultra HD video. I don't think I've experienced that yet. Okay. So if you want to stream video files, I'm going to cut through this quite quickly. So I'll skip through this quite quickly. Two standards, FLAC and ALAC. And if you check these out, ALAC is related to Apple. Examples of open source lossless compression formats. So it's lossless, and file sizes can be reduced up to 50%. So it's lossless, can compress up to 50% without losing quality. How's that possible? Right. 1400 kilobits per second wave file can be compressed to 64 kilobits per second MP3, and MP stands for Moving Pictures Expert Group. It's MPEG, short for MPEG-3. By losing some data permanently, so it's lossless, and the bit depth is also reduced to remove unnecessary data, or maybe data that's actually necessary for high quality. I mean, you've got to critically look at these expressions, remove data. In a lossy compression, you're going to vary the bit depth. The amount of data that's being considered was present in the original, and you're reducing the virtual bit depth in playing out or transmitting an MP3 file. So MP3 and AAC, and for the life of me, I can't remember what AAC stands for. Patent codecs, these are compression and decompression systems. And famously, because it's used by a market leader for transmitting entertainment, Og Vorbis. Og Vorbis is an example of an open source lossy compression technique. So you might want to check this out and see it's being used currently by a major commercial concern. So in summary, a sample rate is the number of audio samples recorded per unit of time. Bit depth measures how precisely the samples were encoded. And the bit rate is the amount of bits that are recorded per unit time. Bit rate is the amount of bit information that are being recorded per unit time. So again, bit depth is the number of bits available for each sample. The higher the bit depth, the higher the quality of the audio. Bit depth is usually 16 bits. 24 bits maybe on a DVD. Okay, so it's giving you fairly general picture, and just reading through this, I'm just sort of wanting to give much more information than much more explanation than I've given, but you can use it as a sort of like a rough map. Good to see you, Roger. Pleased that you're present. Sorry I didn't see your message earlier. So codecs are programs that encode or decode audio, image or video file. And compression codecs are aimed at reducing the size of a file without affecting the quality of the original too much. And algorithms will decide the amount of data that can be removed so that Chris Kinberg doesn't notice. You know, Chris Kinberg can't see very well and can't hear very well. You know, got a particular Chris Kinberg algorithm which can compress a file which is perfect for the ears and eyes of Chris Kinberg. I'm only joking. Don't worry. So we're moving on a little bit. We want to look at run length encoding, otherwise known as RLE. And it's an example of a compression algorithm that converts consecutive similar values into a code. And the code consists of identical values and the given number of times this value is repeated. And it's lossless. So I'm going to show you some run length encoding, and I think you'll see straight away that it's lossless. In other words, given a compression, I can always work back to the original without any loss of information. So have a look at this. I think it's an 8x8 grid of squares, coloured black or white, but not both. And each tile could actually conceivably be coloured with a third colour, or fourth colour, or a fifth colour. Or maybe the grid is 128 by 128 and you want to compress the data within that coloured patchwork of tiles. Anyway, what I'm doing here is to represent a white square by 1 and a black square by 0. So I'll have a black, black, white, 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 black. And I can represent that by 2 occurrences of 0, 2 occurrences of a black square, followed by 5 occurrences of a white square. Here I've got 5 squares of white, followed by 1 occurrence of a black square. And that, to me, perfectly represents the information that's actually being shown in the first line of this 8x8 grid. 8 columns, 8 rows in the first row. The second row could be equally easily represented by 116011. So you might think, well, if the data that you can see here and now was to be represented pixel by pixel. Like here in the top left uppermost corner, I've got Cartesian coordinate 0, 0. I've got a pixel that's black. So I need quite a lot of information just to represent that bit of information here. And then I'm repeating that. I mean, maybe I've got how many? Uh, let's say, just for the sake of argument, 64 different pixels in this single tile. I need 64 descriptions of those pixels, and then another 64 for this tile. I mean, the information given in this image is quite huge. It's quite a lot of information. But I can reduce it simply by giving you some key for how to represent each unit of visual data, and I'm going to specify squares by the number of occurrences in a row. And that this line here, believe it or not, represents a huge reduction in the information I might have been tempted to give you. I mean, probably useless information, because I'm just repeating information about 64 pixels again and again in the same row. So you're going to have to make up your own mind about this. The type of coding is not efficient if the file doesn't have many runs. What do I mean, many runs? No idea. What is it to run? I don't know. I'm not sure. And in such cases, the file size may increase instead of getting compressed. And RLE is thus used only in simple images with a large area of similar colour. Well, I'm going to leave this out. I mean, I've introduced you to the idea of the actual encoding, and I'm not here to critically assess each way of compressing a file. But run length encoding could be used to compress a video, because if you think about a video, there's a lot of repetition of data. For example, I've got I'm showing you 5 images within a single video, and they're all identical. I mean, look at this circled area. It doesn't change. So what does change is maybe the position of this yellow automobile as it moves. I'm assuming it's moving at could be moving at high speed, could be. The positions of these cars with respect to the road it's on are changing. So you can think of how you can compress all these 5 images by simply saying, well, the data in the area that my cursor is crossing doesn't change. It's the same. I don't have to store all this information 5 times. However you're going to do that. I'm just saying, look, I'm taking this strip, which accounts for about 1/8 of this frame, doesn't change. I only have to save information concerning that it's repeated 5 times. However, the data concerning this yellow shape is actually changing position. But there's still a core of the car that remains the same, I guess. Okay. So finally, we move on to Huffman coding. And it's this that I want you to pay particularly close attention to. It's important, and it's very much of an A-level sort of question that you get on formal exam papers. And if you're at university, I remember Huffman coding being taught during the second year at some point, although in a far more detailed way than I'm going to present it now. Right, so Huffman coding. It's a compression technique used to reduce the number of bits that represent each letter in a body of text. And ultimately, I'm going to create a binary tree that will enable me to encode letters and to decode an encoded sequence of letters. So Huffman coding allows me to compress losslessly data, and Huffman trees enable me to both encode data and to decode it at the other end if I'm transmitting it. So I remember talking about binary trees, although on that occasion there were just a couple of people present, so you might have forgotten what a binary tree is. But so I'll remind you in a moment or two, but I don't want to. First of all, I want to show you part of the ASCII encoding scheme. I mean, ASCII letters are used to represent characters inside a computer or inside in a transmission of data process. So ASCII is very widely used, and it stands for American Standard Code for Information Interchange. In other words, you're sending data, or you're showing data. Here is a way of encoding that data, character encoding, right? And there's an alternative to ASCII, and that's EBCDIC, and that's very much talking about IBM mainframes, and that's how IBM mainframes, which, I don't know how many there are today, but how they represent data internally. So, quick looking at this, I've got the letter C. In fact, it's the capital C here, and it's got an ASCII code of 099, which is a binary. It's being given a binary equivalent of 011000011. So this letter C, capital C, actually needs these 8 bits to represent it. Okay. So as a quick question to you, is this binary number equivalent to this number here, 103? Tell me. And that represents the letter G, I think. Okay, no, am I gone crackers here? Capital C. I'm getting confused with it. 000. Capital C, lowercase c. 10011. 1000011. Same binary code for these two different letters, lowercase, uppercase. ASCII code 99, ASCII code 67. Same. No, they're not the same binary numbers. So, okay. So lowercase has got 011, prefix of 011. Uppercase has got a prefix of 010. Okay, so hopefully when I say that if we want to represent some text by means of ASCII, there's an implication for storage because each letter requires 8 bits of storage. So let's carry on. So there's EBCDIC, which I mentioned. So in ASCII coding, each letter is represented not 8, 7 bits. It's got a leading 0, in fact. So the letter C, lowercase is 011000011. In Huffman coding, each letter is represented by means, sorry, each letter is represented with a different number of bits in Huffman coding. So I'm going to code up each letter, but it's going to be a different encoding from an ASCII encoding. And I want you to know that the most frequently appearing letters are represented with fewer number of bits than those letters that are being encoded with um, uh, lower frequencies. So most frequently appearing letters are going to be represented with fewer bits than those with those characters that occur less frequently. And if we choose this general sort of encoding, the number of bits required to store data is going to be reduced. And let me try and prove that to you. So, just for a laugh, consider the sentence, Betty ate butter. And I'm going to count the frequency of each letter and record them in the table. And I reckon there are 16 characters in total within that sentence, excluding the inverted commas. So including the spaces, I've got 16 characters. Count them up. Right. Therefore, the total number of bits used to represent their ASCII codes are 16 times 7, because you need 7 bits to represent an ASCII code. I said 8, but there's always a leading 0. Okay. 16 times 7, which I think, according to my best mental arithmetic abilities, is 112. You've got 112 bits. You need 112 bits to represent 16 characters. So let's consider a sentence again. Better ate butter. What I'm going to do is to assign a binary value to each letter. And remember, I'm going to use more bits if the frequency is low compared to letters like T, which occur, in fact T occurs most frequently, and I'm going to represent it by means of a 1 bit as opposed to 3 bits used to represent a character with a least number of occurrences. B is like a halfway house. B has 2 occurrences, and E has 3 occurrences, and R has 1 occurrence. So these 4 letters, A, R, U and Y, have the same number of occurrences, and I'm assigning them the same number of bits, so 3 bits. 3 bits. And of course, if I've got 3 bits, I can certainly represent 1, 2, 4 letters easily. I've got 3 bits, I could represent as many as 8 equally occurring letters. I've just got 4 equally occurring letters, A, B, U and Y. And I've also got 2 occurrences of a space. And so I've got 2 occurrences of space and 2 occurrences of B, and I'm going to assign both B and space the code 10, 2 bits. And I'm going to represent E and T with 1 bit. I'm using 1 bit for T because it's got the most occurrences, and I've got occurrence of 3 occurrences of the letter E. So I'm going to represent that by means of 1 bit as well. And so using a binary tree, and remember a tree is a tree with a single node. There are no cycles in the tree, and every node, every internal node of a tree has no more than two children. So I've got two. T has got two children. One of its one of its children is a node, an internal node, but never mind. This internal node, so it hasn't got a name, or I'm not using it to store data or anything like that. It's got two children, two children, A and R. And E has got two children. It's got a space as a child, and it's got a subtree as the second child. And this node has got two children, and the children are U and Y. If I assign arcs coming out of a node, the left-hand child, I'm going to put a 0 on the left-hand child arc and a 1 on the right-hand child. And you can see that starting from the node, if I follow the path 0, 0, I'm actually going to come to node B. Look, node B. If I represent, if I've got the code 0, 1, I'm not going to end anywhere, but if I've got 0, 1, 1, I'm going to get R. So here we are, 0, 1, 1. And a single 0 is going to take me to T. Here it is. I'm going to encode that node, the letter T with 0. Letter E, I'm going to encode with a single 1. Here it is. 3 occurrences of that. And so on. And I'm going to show you how to systematically build this tree in a moment. But the idea is that each of the leaves of this tree, as well as a couple of internal nodes, contain characters, and the path taken to get to a particular node is going to represent its coding, its encoding rather. So T is going to be encoded with a 0, B is going to be encoded with a 0, 0. This node is going to be encoded with a 0, 1, 1. And A is going to be encoded by the sequence, binary sequence 0, 1, 0, and so on. So you might think, well, the only other thing I want you to notice from the table is that, once again, I've said this already, the most frequently occurring letters have got a relatively low number of bits representing them or encoding them. So T has got 5 occurrences, and I'm encoding it with a single bit. On the other hand, A has only got 1 occurrence, but I'm encoding it with 3 bits. B's got 2 occurrences, which is certainly greater than the number of occurrences of B, but I'm encoding it with just 2 bits, and so on. And the idea here is that when it comes to writing out the code for our sentence, I've got 5 occurrences of T, and I'm going to encode T with a single bit. Now that's a bigger saving than encoding the number T, 5 occurrences of it, and that's going to take, if I'm encoding it in ASCII, if it's an ASCII encoding, I would have had to have used 5 times 7 bits, 35 bits. But here, if I'm using Huffman coding, I can, and I represent each T by a single bit. To represent 5 occurrences of T, I'm just going to use 5 bits. They're all zeros. So there's an economy. The most frequently occurring characters are going to be represented in Huffman coding by a fewest possible number of bits. Okay, so Huffman coding, substituting the values I've got in the sentence and calculating the total number of bits, I get 28 bits. So if I'm using Huffman coding, I just need 28 bits. That's compared with the number of characters 1, 2, 3, 4, 5, 6, 7, 8 multiplied. What's it? 8 multiplied by 7. 7 eighths of 56. Why have I got 112 here? If I'm using ASCII code, I've got 1, 2, 3, 4, 5, 6, 7, 8. 7 eighths of 56. 8, 7, 8, 7, 7's of 49. Oh well, I don't know. This was supposed to be a representation of how much bits I could have said, and it's going to be. I mean, all you need to do is to write out how many bits you need to use for each of those words in the sentence, multiplied by 7 bits, and I think it's 7 eighths of 56. Okay, so somehow 56 has been transformed into 112. I don't know how that happened. So I've got something like 56 minus 28 bits. I've got a saving of 28, 56 to 56, 32. So I've got divide 32 by 84 and it'll give you the percentage saving of bits or percentage of decompression that's possible. So I'll leave you to just check that and remedy that. Should be quite straightforward to do. So I'm left with this table anyway, and so how do I build the binary tree? And the idea is that we need the lowest number of bits for letters with a larger frequency. Therefore, we must award a slightly greater number of bits for letters with lesser frequency. Because it doesn't really matter because I'm using those far and few between, but I'm using the letters with higher frequency most often. And if I can minimise the number of bits those used, then I'm going to get some sort of saving. So I've got 4 letters of frequency 1, and I've put them here because I want them to occur as the 2 children of a particular node. So I need 2 subtrees to represent 4 letters. I hope you agree with that. I've got 4 letters to put into the tree, and the only way I can, or the best way I can do that, because on the grounds that they've got the same frequency 1, I can just have subtrees consisting of the 2 children, and 2 children for this subtree. These are the 4 nodes I've got to deal with. And I've now got to consider B and the space, which have a frequency of 2. So I can put these above the subtree representing these 2 less frequent letters. So it's the distance through the tree that's going to indicate the relative number of occurrences. So B's got a higher occurrence than either A or not. It's got an occurrence of 2 compared to 1. So I can put that here. But I can also put space and join that onto the tree constructed from an internal node, this internal node, having 2 children. And the first child is space, and the second child is a subtree consisting of U and D. And it's the distance up the tree, going higher and higher than trees, representing increase of frequency of occurrence. Um, Finally, I can consider it, well, not finally, I can consider E, which has a frequency of 3. So I can actually put that, replace the internal node here with E. So that's got a frequency of 3, that's got a frequency of 2, that's got a frequency of 1. Those two have got a frequency of 1. And it's a sort of almost a function of the distance you have to go up or down the tree that's going to correlate with the number of the frequency of occurrences. I mean, I could have put it here if I'd wanted to. I've got a choice here. I could have written E here, no problem. So the letter T has the highest frequency. It has a frequency of 5. So I could include T here. Why have I got... hang on. So let's just check that. Why have I got space here, but E here? So something gone slightly wrong here in my building a tree. And I reckon... not sure. Because this doesn't accord with the rule I set out. The higher the tree you go, the higher the less frequent the occurrence becomes. But we'll see what happens. We're going to put T here. So we're going to put T here. I'm going to put T here. E has a frequency of... oh no, that's okay. Oh goodness. So I'm actually saying that even though T has the most occurrences, E has the next number of occurrences, which I think was 3. So going up the tree, you're looking at you're looking at increasing numbers of occurrences. So I'm going to put T here, and T and 1 both have a higher number of occurrences than space or B, and especially have a higher number of occurrences than A and R and U and Y. So does this all work out? Let's have a look. So that looks reasonable as a way of representing things, but okay, so the final step. So I've taken into account every letter, and I'm going to join these two subtrees together by means of the root node. And here's another subtree, and I'm joining it to the main tree with root. This is the root. And each path through the tree terminates with a leaf. And there's some internal nodes. Disregard those for a moment. Left branches are going to be assigned 0. Right branches are going to be assigned the value E. So what this tree enables me to do, because I've built it according to what I really needed, I can assign to B the code given by its path. So it's 0, 0. And the code for A is going to be 0, 1, 0. And the code for R is going to be 0, 1, 1. And the code for space is going to be just 1, 0. And the code for U is going to be, going to give it the code, going to give this character the code 110, 110. Now, what I've done here is to ensure that the codes I give to letters that have relatively few frequencies, more bits in representing them. And for the next level of occurrences, I'm going to give just 2 bits. 1, 2. Here I've got 2 leaf nodes with 3 bits representation. I'm going to represent space by means of 2 bits, 1, 0. I'm going to represent the character U, this leash node, as 1, 1, 0. And so I think I've got all this. I think this table has been, in a sense, generated by the construction of the tree, because I've got all the codes for all the letters, which are written in this row here from the tree. So for T and, is it T and D? T and E. Oh, okay, no, T and E. I just need 1 bit to represent them. Okay, so they're equally, I can't remember how many times E and T actually occurred. I think E occurred fewer times than T. This was 5 times, this was, I think, 3 times. But I'm representing the 2 most frequently occurring letters by a single bit of information. Okay, so this is an example to used Huffman coding. There will be a different character coding for each letter. Okay, so that might all sound a bit complicated, but you can work it out for yourself. How is a Huffman tree used? One quite interesting reference is this, for lots of different examples. And how do I use it? Well, let me try and explain, but I'm not entirely satisfied with this explanation. Supposing I'm receiving this sequence. This is my first, second, and then as a second input I just get a single input, and then another input, and then another input, and then an input consisting of 1, 1, 1. Supposing I receive that from left to right, what I can say, okay, well I'm being given a 0, 0 input, and a 0, 0 is B, so I put the B here, and then the next input is 1, so I look at the table and I get E, so I write E, lowercase e of course. Then I get T and T. How do I get that T and T? 0 and 0. What's 0? Let's have a look at 0. Single input, 0. It's T. Then another input, 0. It's T again. And then I get another input, 1, 1, 1. 1, 1, 1. Gosh, that's a Y. So I've got the word Betty. Then I've got a space, which is should be a 10, 0. Where does that appear? I think I've missed that out. Never mind. But hopefully you all get the idea. Now the only problem I can see with this is that to use the tree as a way of decoding this bit sequence, I need to be told that the first input ends where this space is, and the second input ends where this space is. Because otherwise, I'm going to look at the first 0, I'm going to say, oh, I've got a T here, rather than a 0, 0, which gives me a B. So I need to be told that I'm going to input 0, 0, then I'll have a space, stop. I've got an input, 2 bits input, and I can use the tree to convert that to the letter B. And separately, I'll get a bit 1, and that gives me an E. I'll write the E here, then I've got a space, a 0. That definitely is a T, write the T. Another 0, separate input, got another T, write the T, and so on and so on. So hopefully, wait a minute, why have I got, I'm not sharing. Hello guys, I didn't intend to do that, and I don't want a recording with my picture on it, so I'm going to, oh no, you can't see that, so it's alright. So hopefully, and this is the important bit, you can see that using what I've done so far, I've got a lossless way of decompressing sentences. And I've given you an idea of the compression rate as well. And I can use the tree as a way of decoding. In fact, I could just use the table. I mean, if I get a 0, yeah, I can put this A in here, A10. But I need to be I need to understand that codes are actually going to be, I'm going to be told when the input ends. Here I've got an A10, end. I can convert that into the letter A. Here I've got A10. So I need the different codes for the letters to be separated by a space. That's my only observation here. But if you check it out, I can recreate the sentence perfectly. And I might have forgotten to put a space in. I should have got a 10 here. Should have put in the code for a space. So I can't change that on the fly, but just be aware of it. Okay, so try this at home in the safety and comfort of your home armchair. I want to give a Huffman encoding of this string of characters. Here's the list of frequencies. Here's the tree, the resulting tree. And I can actually look at the incoming code. This is 00. So I get a 00, which is an A. And I get following a 00, I get another 00, which is an A, another 00. So I get a sequence of 5 A's, and then I get a B. So I can't quite see how a B is represented, but I've got is it what's a B? I don't know. A B is represented, but I don't know. But you just try it out. Make sure you can understand this. Okay, so I'm stopping there for this part of the session. Hopefully I've introduced you to some of the important aspects of compression, of different sorts of things. Compression of text, compression of video, compression of audio. What we haven't really spent a lot of time on is the actual physics background of sampling analog data. But I think I've given you enough information to understand how, say, the sampling rate or the quality of the sampling data can give you quality in your video or your audio. And it's the rate at which you can process or show the system user of all the video frames per unit time that adds to the quality of the video. You're not going to have gaps and jumps, and you're going to have continuity, and you're going to have a lot of detail. So I'm going to take that down, and what I really should do is to now show you your coursework, your intended coursework. So I'll just retrieve that. And as I said, it's not in final version, and I might actually include something on Huffman within that, but we'll see. And for all I know, you might have even been asked the same questions already, but I'm not too bothered by that. So, um, I haven't decided on a submission date, but I reckon it's in a month's time, and I certainly haven't issued it yet. What I'm issuing will be, uh, this is certainly a provisional problem, a provisional assessment paper, and I'll finalise it in the next couple of days. Oops. Right. So the first question, and I can almost hear groans coming my way, is on the synchronization problem. And I want you to tell me what the synchronization problem is and why, in certain circumstances, a given digital system A will not see a signal sent to it by another system B. And I want you to, in order to make your explanation clear, use your own words, and I want to have some analysis. Give me a diagram. Give me a diagram to help your explanation and analysis. And in a moment or two, I've actually got the diagram that I want you to refer to. All right. Thirdly, because I haven't looked at one yet, thirdly, I want you to explain what is meant by a full handshake and why on earth you need such a thing. Why do you need it in the first place? And I do remember talking to, trying to give you an intuitive understanding of a handshake. And I'll go through that once again in a moment. But I've actually formally given you an example of two systems communicating by means of what in effect is a handshake. And that occurs, the diagram for that occurs in a document involving the word synchronization. But if needs be, I can actually tell you what the document is that you should look at. So why do I need a full handshake? A full handshake, because apparently there are lots of different sorts of handshake. A full handshake in the case of human beings follows like this. I raise my hand in front of me and keep it raised for as long as it takes for you to see it. When you see my raised when you see my raised hand, you're going to reply by raising your hand. You're going to not necessarily touch one another's hands, but you're going to raise your hand as though you're going to shake my hand. And you're going to keep your hand raised for as long as it takes me to see that you have raised your hand. At that point in time, I'm going to lower my hand. And in that way, I'm sending you an acknowledgement of the fact that I've seen you attempt to make the handshake. You want to talk. And when you see my lowering of my hand, you're going to lower your hand. And the lowering of your hand indicates to me that I have seen. It's going to indicate to me that you have actually. I'm actually acknowledging your acknowledgement. You've lowered your hand. And that's okay. You're acknowledging the fact that everything. Oh, I can't remember. You've got to fill in the steps a little bit. Right, question part 1 is this. Explain why, if a digital signal changes its value from 1 to 0 or from 0 to 1, this must have taken place at a time prior to t setup units of time before the arrival of a rising clock edge in order that, for example, a memory device such as a D-type flip-flop sees the signal and can memorize it, can capture it. What other constraints on the signal changing must be respected? Right? So it sort of seems semi-technical, but that's only because of the word synchronization. In the world of digital systems, it's very important that if I communicate to you, you need to see my signals, and typically one of my signals will be to request a service from you, and I'm going to keep my request signal up or on or at logic 1 until I see you give me an acknowledgement. And the acknowledgement is not only the fact that you've seen my request, but you've actually done something on my behalf. And when you send me an acknowledgement, I'm in a situation where I can pick up the data that you've sent me. So there's lots of, if you look up the synchronization problem, you'll find lots of, have I got it here? So, no, so this isn't right at all at a minute. So I'm going to, what I'm going to do in a few moments is to show you some diagrams which relate to the solutions of question 1, but I haven't got them on this paper. Well, the second question, and I don't think I've asked you this question ever before, but I do know that we have done some work on sorting, and I want you, it's very straightforward, very easy this. Aren't I being kind and nice? Explain the bubble sort algorithm informally, in your own words, by referring to an array of unsorted integers, and use a diagram showing me the operation of the algorithm. Okay? 10 marks, that's a quarter of the marks that you need to get a bare pass in this paper. And I want you to tell me how you could implement bubble sort using either pseudocode, that's like a halfway house towards programming code, or in a high-level language such as Java or Python. And I'm going to add something to this question and just explain the code line by line. In fact, you can implement bubble sort in, I think, 3 or 4 lines. And the only difficulty you're going to have is to express the fact that you are repeatedly scanning each, you're going to scan the array each time to make various changes to the array repeatedly. You're going to make changes once, you come to the end of the array, and then you're going to start at the beginning of the array, go through it again, make the changes necessary, come to the end of the line, the end of the array, then you start for a third time. How do you do that in code? How do you repeatedly do all this? You repeat the operation of repeatedly going through the array, making changes. And you're going to repeat going through the array for length of the array number of times. And hopefully I'll be able to show you something on that in a moment. Okay. The algorithm involves swapping array elements where appropriate. Can you provide a suitable swap numbers function in Python using tuples? Well, if you have a look at the notes that I've given you, it's actually the document I've given you on tuples, and right at the end of that document there's just three lines of code where you can a single line of code, which in Python just swaps two elements around, and the elements are actually going to be, sorry, I'll repeat that. It takes two elements of an array and swaps their values around. So if I've got array element number 1 and array element number 2, it's going to swap the value of array element 1 and put it into array element 2 and put the value of array element 2 into array element 1. You can do that in one line in Python. Check it out. Okay? And this I don't know about. I'm going to have to think about this, but it might be easy for you, or it might be, are you really going to learn anything from doing this? I'm not sure. I'd rather, at the moment, replace it by a question on Huffman coding. So be prepared. But the question as it stands is, using a my language is breaking down at the moment. Using a copy of a modified version of the echo server.java and echo client Java and simple proxy server.java programs I have given you and will give you, run each of these three programs concurrently in Eclipse and ensure that the first is capable of communicating with the third by using, let's say that the first of these can communicate with the third, and the third communicates with the first on TCP. Oh, I don't know. Well, that will have to change. But I just want you to pay particular attention to the port numbers that these three programs use. And if you remember from the work we did on TCP, if you use the Java connect method, you need to specify an IP address, which in our case is going to be 127.0.0.1, and a port number. But I want you to match the port number on which the port number that you create on the. Okay, dear. So I'm right. The first program is echo server, and the second is echo client. So I want you to make sure that the first can communicate with the. This is great fun. The first program communicates with the third. So which is the third? And the third communicates with the first on port 99. So the first communicates with the third. That's the echo server. Communicate. Well, okay. Well, the idea is that I want to make sure that the echo client communicates with the proxy server, and the proxy server can communicate on the echo server by choosing the ports properly. You've got to make sure that they all talk to one another. So it's just a question of conceptually running three programs and allowing them to communicate with one another. And the idea is that you using the client is going to type something in, and that message is going to be passed to the proxy server, and the proxy server is going to send that to the server. And I want you to explain how the proxy server behaves both as a server and a client. So that needs just a little bit of thinking about. Worth 5 marks, and we can talk about this question again later if needs be. I'm asking third part. Are communications between the echo client and the echo server concurrent? Can they take place at the same time. In other words, can the client talk to the echo server via the proxy server at the same time that the echo server is sending messages back to the client via the proxy server? Anyway, I'm not going to talk about this anymore because it needs to be just sorted out a little bit. And in any case, I might replace this by a question on compression using Huffman coding. So we can discuss. We've got all next week to discuss what I decide to change over the weekend. So here's a question on data structures, and it's quite a long question, but it's very straightforward. Explain a stack. What is meant by a stack of objects of type string? So you want to stack strings and refer to arrays of objects of type string and the operations of peeking, pushing and popping the stack. And methods, I think that should be, that determines whether the stack is empty or full. And a method for returning the actual size of the stack. Set out the pseudocode or Java for implementing the stack and operations. Well, in fact, I've given you the Java for all this. We had an hour session. Yeah. That's all right, but you know, God willing, there will be a full recording of this. I'm making I'm making a recording my end, but I'm making a BBB recording as well. But that's been extremely unreliable in the last 2 weeks because it just doesn't give me the recording. So somehow or other, I'll get you a recording. So don't worry about it. Okay. So good. Take care. Bye bye. Yeah. Bye bye. So data structures. I'm asking you about stacks. And we've had a full hour's presentation on stacks and given implementation of all these elements in Java. I'm not quite sure. What I'm really saying is, well, okay, forget about the pseudocode. I need some Java and a bit of explanation of what you're doing. So if you can comment on how you've used the Java, what the Java that I've given you means. And then step 3, I want, if you're given a stack consisting of these four strings, use Eclipse to show me the result of executing pop, push and peek operations by showing me a screenshot. And finally, so it's quite, it needs a bit of concentration and thought, but it's all doable. And it's all quite understandable, even if at the first sight it all seems a bit tricky. So the fourth part of the fourth question is, explain what operations you need to build a queue of integers. Right. And I want you to tell me how you enqueue an integer onto the queue, how you put something onto the queue, and how you take it off. And what I'd like you to do, so I might write this in as a hint, give me a diagram of what's happening. Give me a diagram of what a queue looks like. And it's something I've shown you before, and the vital document is that at the end of the document on threads, I've got a couple of diagrams, which I showed you very recently, because I was talking about a synchronized keyword to get mutual exclusion, because there's a potential problem if two threads simultaneously try and put an object onto the front of the queue, or 2 threads or 3 threads all decide that they want to take something away off the queue at the same time. There's a problem. Okay? So again, this is something you can think about for next time, and if you have any questions, then you can ask me them. All right. And finally, so this is um, um, sort of half non-technical, and it's like a brief essay. What steps do social networking websites take in order to filter abusive, violent, and misleading content? For example, misinformation. Are these adequate? And who does what? Do a little bit of research and enjoy it. Find out about what these companies' responsibilities are or should be and what they're actually doing. And then state what is meant by HTTP and briefly state the role of HTTP in enabling, I should put enabling, not allowing, a TCP client to communicate with a TCP server, like a web server. So it could be a web browser and a web server. TCP client, TCP server. Maybe I need to request a web page. How's all that done? Not too much detail. Just show me that you understand. And is it true to say that HTTP is a simple request response protocol? And give an explanation. And then finally, describe how jitter and end-to-end network delay can be mitigated using a client-side buffer in case of an internet phone which uses an unreliable protocol but whose packets have been time-stamped at the sender, and explain how talk spurts can be transmitted and at what rate they should be sampled. So in fact, that's quite a lot to do, and I might chop out the HTTP bit. But as I said, all that's provisional, and the key diagrams for the last question, 5, is this and that, which I'm sure you'll never have seen. What? What? Has everyone left me? Oh dear, oh dear. Oh my goodness. Farhath, are you still here? Farhath? Farhath. So you left at 3:27, 3:30. Is that right? Okay, well, I'm going to terminate this session and I shall talk about the internet transmission of media. And hopefully you will have got a lot of information.